Go.
Okay, so here we have a related rates problem, and related rates is a concept that has to do with implicit differentiation, but now we're going to have a bunch of different variables, and we're going to differentiate them or see how they change in terms of another variable. Usually in related rates, it has to do with time. So for this example, we have a trough is 10 feet long, and its ends have the shape of isosceles triangles that are 3 feet across the top and have a height of 1 foot. If the trough is being filled with water at a rate of 12 feet cubed per minute, how fast is the water level rising when the water is 0.5 feet deep? So that's a lot of information altogether, but it's a lot easier when you break it down into steps. So the first one is going to be to draw a picture. Visualize what you're looking at and what you have to find. So I drew the trough here, the water inside, the tick marks represent the isosceles triangles, and then they gave us this extra information about the triangles on the end. So I kind of blew this one up here, and they told us that the base of that is 3 and the height is 1. So any constant number that they gave us that will not change and has to do with the trough and not the water, I've identified over here. So 10, 3, and 1. Once you have a picture, the second step is to find some formula that relates everything together. So in this case, we're talking about water being filled in a trough. So ultimately, that's the volume of the trough. We don't really know the formula for a triangular prism, but we can use some intuition and say, okay, we know the area of this triangle, which is going to be 1/2 base times height, and if we multiply it by the length, that's going to give us this 3-dimensional figure, which will give us a volume. So I just went ahead and multiplied it by 10 instead of length because it's a constant number relating to the trough that's never going to change. So you can simplify that to 5b times h. The third step, once you have your formula, is to go over to the side, and any variable you have in this formula, you're going to write. So we have a v, a b, and an h. And for every variable, you want to have the derivative of that, so a dt. So we'll have our dv dt, dv dt, dh dt. The next step is to go through the problem and to identify any of these values. So it says, if the trough is being filled with water at a rate of 12 feet cubed per minute, okay, that's talking about the water being filled in the prism, which we already said was related to volume. So it also says being filled at a rate of 12 feet per minute. So we know that's going to be our derivative and not our volume. So I've identified our dv dt as 12. Then it says, how fast is the water level rising? Okay, they want to know how fast this height is changing. So the rate of that height, not necessarily the height. So then I put a question mark here because this is what we're trying to find, the rate of the height. So when the water is 0.5 feet deep, we have our height is 0.5. Okay, so we can tell we're missing a bunch of variables here. A few things to note. In terms of these variables, not the derivatives, it's okay to be missing one if it's isolated in this formula. So for example, the v, when you take the derivative, it'll be just dv dt, and the v is going to disappear. So it's okay that we're missing this one. Our b might give us some problems, but let's hold off on that and look at our dt's. So the rule for dt's is you can never be missing one. You either have to have it or be looking for it. So we can tell in this problem we're missing our dv dt. What do we do with that? Well, we can't really find a rate if they don't give it to us and we're already missing one. So what we're going to do is if we get rid of b, then we'll never have to take the derivative and we'll never have to know dv dt. So what we're going to do is get rid of b. So the question is, how do we get rid of b? That usually has to do with the extra information they give you in the problem, which they gave us about this triangle over here. So what I did was I set up a proportion. We wanted to get rid of b and the base, so I set up a proportion in terms of the base. So base over height is 3 over 1. We isolate b and we get that the base is 3h. We can immediately substitute that into our formula so that we get, once we simplify that, b is equal to 15h squared. Now that we have our formula completely simplified and every variable we have in here we know the value of, we can finally differentiate. So we take the derivative of v. All of these are going to be in terms of time, like we said at the beginning. So v is going to be dv dt. Then we take the derivative of 15h squared, which will give us 30h. Don't forget your dh dt, because that's also in terms of time. Then, once you differentiate, you can plug in any values that you know that we identified over here. So dv dt is 12, 30 times h is 0.5, and we're looking for dh dt. Once we simplify dh dt, we're going to get that it's equal to 4/5. So the last thing you don't want to forget is your units. So we're going to go back at the question and try and figure out, okay, we just found what DHDT was, but what were we really looking for? So like I said earlier, our DHDT was how fast the water level is rising. So our water level, or our height of our water, is right here. They want to know how fast that's changing. So that's going to be the rate of our height. And that's going to be in terms of the same thing they identified the volume in. So 12 feet cubed per minute, that's our volume. So our height is just going to be feet per minute. And that is going to be our DHDT.